Okay, so now let's start writing this function that computes the time derivative. Let's just call it ddt2d. Okay, and first thing we are going to do is assign the output to be dwdt and the inputs to be time, which we don't need, and the state variables. And here we actually need more information than just the input, because we have the geometric information, so we'll use the global variables that's already populated in outside. I think I have the itry and the normal that I need, and also the area. Right, that's the only information I would need about the mesh. All right. So n, the number of cells, is the dimension of our discretized equations. Right, that's the number of control volumes. Should be the length of W divided by 3, because we have 3 variables, h, hu(x), and hu(y). And let's make it dwdt to be zeros n by 3 to start with. And every time we compute the flux on the on the interface, we're going to subtract it on one of these dwdt's and add it to another dwdt. Which is, so after we compute it, basically I'll leave some space in between, but we are going to be loop through the interfaces, which is the length of the normals. Well, it's not the length of normals, but the size of normal in the first dimension. The length of normals would be twice that much, because it has x and y components of the normal. And after I compute the flux, I need to, so if I compute the flux Fi, then I would be adding it on one side and subtracting it on the other side. So dwdt of, okay, so I have to know which are the triangles on the two sides. So T1 would be equal to itry of I1, and the T2 equal to itry of I2. And so for T1, the flux I want to compute is going to be from T1 to T2. So T1 has to be subtracted minus Fi. I have to divide by the area, right? Area of T1. So that's because in our finite volume scheme, the area is multiplied on the dwdt. Okay, and also dwdt of T2 is equal to dwdt T2 plus Fi divided by the area of T2. So that's how we accumulate the flux into finite volume, into the control volumes. So here there is actually a special case. Is what if the interface lies on the boundary of the entire domain? Well, if the interface lies on the boundary of the entire domain, in the code of computing, the itry actually set itry I1 equal to itry of I2. So both sides of the interface is the same triangle, right? So that means if it's on the boundary. So basically, I should only accumulate it once if it's actually on the interface. So if T1 is not equal to T2, I would be doing that. Otherwise, if I would only be doing it once. Okay. So now the only task is to compute Fi, to compute the interface flux. And again, there are two cases. If T1 is equal to T2, and else. So if T1 is equal to T2, it's on the boundary, and we know that Fx I on the boundary would be 0 because there is no mass flux, and the x momentum flux would be actually just velocity. There shouldn't be any flux. So well, let's actually just compute the flux at once. So the momentum flux should be both in the xy direction and corresponding to the normal, right? So we have to also compute the normal. Nx is normal I1 and ny is normal I2. So if I'm on the boundary, then the actually momentum flux can be computed by integrating the half of gh square over the volume. So this is actually g over 2. Well, we need to define g over 2 times the height of the water h at T1. Oh, we haven't set h yet. So let's say h would be equal to w1 to n. So that's the first part of the state variable. Ux is w of n plus 1 to 2 times n, and uy is equal to w 2 times n plus 1 to the end. Right, so that's the state variables we have. So h of T1 squared times nx, and the same thing times ny. So that will be the flux. All right. And otherwise, we have to actually use the approximate Riemann solver, right? So before we do that, let's actually compute what's the flux on the center of the cells. So this is assuming we are going to be using a piecewise constant approximation, and which results to a first order scheme. So fx would be equal to h times ux. So that's the first term in the flux, and the second term in the flux is hux squared plus half gh squared plus g over 2 times h squared, and the third term is h times ux times uy. So the y flux is basically almost symmetric. So ux times uy, and the plus term goes into here, and this is uy squared. Right, so that's the x1 and y flux according to the differential equation. All right, so then here, what we have to compute first is the average between the cell fluxes. So we have to compute the f of, let's say, f of 1, which is in the triangle 1, right? ft1, let's say, is equal to fx at t1, and the column, because it has 3 dimensions, times nx plus fy of t1 times ny. Right, so that's basically the numerical flux. If we upwind all the way to, I mean, if we choose the left side of the interface as the value to be evaluated, and also if we choose the right side of the interface, it's just indexing the triangle as T2. Okay. So that's the. If we average them, we'll just get the central flux, which we know wouldn't work around shockwaves. So we have to add numerical dissipation. So to compute the numerical dissipation, we have to compute what's the speed of the wave, actually, what's the speed of the water in the normal direction, and add it with the square root of h times g, right? So okay, so we'll need to compute wave speed in the cell 1 is going to be equal to, let's say, it's going to be ux t1 times nx plus uy t1 times ny, and divided by square root of well, let me just compute it here. N is equal to square root of nx square plus ny square. So here is going to be divided by n, we want to take absolute value of that and then add it to square root of g times h t1, right? So that's the wave speed. That's the maximum absolute eigenvalue, right? We figured out last Friday. So the wave speed, which determines the correct numerical dissipation to add, can be also computed on the other side of the interface. And the total wave speed, the wave speed we want to use is the maximum between these two. All right. Okay, now I can compute my Fi to be the average of the fluxes seen from both sides plus my wave speed divided by 2 times the difference between the conserved variables on one side and the other. So it'll be my W T1 minus W T2. Alright. So now I have completed the computation of all the fluxes. And I already accumulated the fluxes onto the dWdt. So that's the complete finite volume implementation for unstructured mesh. Of course, we are still first order, but like it's going to second order. Just it's more like it's more work in finite difference rather than in finite volume to get to second order, right?